Hello, welcome back to the continuing lecture in investments. In our last video, we basically discussed, what convexity is and why it is needed, and how it is related to a duration, and by association, it is also the second derivative of the bond price. And because they are, the reason that they are, basically derivatives of the bond price is because they are functions of, bond price is a function of interest rate, right? It's a function of interest rate. And when a function of and as the function of interest rate, right, it is differentiable with respect to interest rate, right? So that was why the duration could be differentiated, and the result of the first derivative of the price, and then the derivative of the duration is the convexity, and convexity is therefore the second derivative of the bond price, right? Now, this looks like a quite a handful, actually. This shows basically how they are all related. First of all, right, the duration, this isn't a modified duration, and we know what modified duration is Macaulay duration divided by 1 plus y. Okay, in other words, it's like discounting Macaulay duration just one period. And if I expand it, basically Macaulay duration is what? This is the definition of duration, just like elasticity, right? And then because this 1 plus y and this 1 plus y cancel out, right? It becomes eventually 1 over b, and d over dy is basically derivative, right? It's the first derivative of bond price with respect to interest rate y, or yield, right? And bond price is function of yield. So if you want to get rid of, suppose you want to get rid of this, 1 over b, what do? Well, you can multiply b on the both sides, and then it will simply become dby over dy. That's delta, basically, change in by over change in y. Now, if you want to review the derivation of modified duration, you can click on this, and it will take you to now, convexity is then the derivative, first derivative of the duration. So if I take the derivative of duration, then d is basically 1 over b, right? It's a parameter. It's a coefficient. So you just you can just move it out, right? And then of course b is a differentiable function, differentiable with respect to y, but since it is just this part, right? And so then it is the second derivative of bond price, right? Duration is the first derivative of bond price, and derivative of the derivative, so second derivative with respect to interest rate, and therefore convexity can be defined as this: 1 over b, 1 over b times the second derivative of b, bond price, right, with respect to y. Now, to get rid of that 1 over b, if you multiply both sides by b, then it will simply be d over d times b, right? Because you multiplied it on both sides, right? You might wonder, if I multiply both sides by b, then doesn't this b cancel out with 1 over b? It's actually, I'm going to show you how the full steps of derivation, and suddenly you might wonder, jumping from this to this, this may not sit in that well in your mind, but I'm going to show you the full steps of derivation. And what I want to point out here is that this is eventually, it becomes, d squared, duration squared, and first derivative of d, and which is, always greater than 0, which is always positive, or, 0. I mean, think about it. Derivative of d is negative. It comes out as negative. Duration is always negative because they mean, they capture the opposite movements. But the squared term of d is always positive, right? So now, first derivative of duration, maybe it can possibly be negative, and if or it could be positive. If it is negative, and if it is, but cannot be greater than, it will be slightly negative, cannot be greater than this. And if they are equal, then it might be 0. But convexity is always positive. And that means the curvature is positive, right? In other words, another way of expressing convexity is, I mean, this is actually the curvature. I mean, you might, what does this mean? You might think, oh, isn't that convexity? No. That's, cash flow, actually. There are many ways to express convexity, many, and this is not actually convexity. This is actually the curvature. I mean, putting a, I would say, putting an equal sign there is a slightly, not the right thing, but because convexity comes from, and what does this mean? This, if I rewrite it, I can rewrite it like this. And from Finance 100, you should know already, Euler's number or exponential function, right? Exponential function is a continuous compounding, right? The basis of continuous compounding. Now, continuous compound, there is only one way you can capture the continuity of this smooth curvature, right? Only one way you can, and that it would have to be through the continuous compounding, Euler's number. And so basically, doesn't this remind you of something? I mean, isn't this like, duration, right? Why this is like, duration is what? Weighted average of, weighted average of the time period, right? Weighted by cash flow discount, present value of the cash flow. And what is this then? In other words, if I go back, I mean, explaining it in words is always lacking, I mean, I don't find words, I find words very verbal explanation always, somewhat, inadequate, because, what can be expressed by succinctly by math to express it in words verbally, it's inadequate, right? It's inadequate no matter what. It's inadequate. So doesn't it remind you of this? Doesn't it remind you of this, right? Discounting, right? Duration is, time period is weighted average times weight, and weight is, 1/4 bond price times, cash flow discounted, so present value of cash flow. So, but in this equation, discounting is discrete, right? Discounting is discrete, but discrete means, you don't have smooth curvature. It's just, always like with the kinks. Now, but then if you express it, in a continuous by continuous, discounting, in this case, continuous discounting, it is like this. Okay, I forgot. Okay, squared here, because now and if you take the as I said, because convexity is the second derivative, it will become, so this is the actual curvature, right? And the actual curvature is, always, positive. What does that mean? That's the definition of, that's the definition of convexity. This curve is the curvature is always positive. Now, so here's the part of the technique that here, when we were here, I said, this is a kind of jump from here to here. And how do we get to that point? So here's the explanation, right? So up to this point, it's already done, so I don't think you have any problem, right? And so we have C times B because of, to get rid of, the idea is basically, if C is like this, but because, because modified duration has this term, right? So in a way, the idea is to cancel out that term, right? But then this cannot be directly canceled out because it's part of the duration, modified duration. But both sides. So anyway, on both sides we have to apply. We have to multiply b, and then our next question is, how do we? Because convexity is the second derivative, right? Then how do we take the second derivative when we have this is like, we have a differentiable function here, one function here, and another function here. Okay, b is also a function, right? Because it's a function of y, right? Remember? So it's like a product of two functions, right? It's like product of two functions. And there are many rules, at least, like, if I remember correctly, it's been a while since I did, very intensely, calculus. A while means, more than actually 25, 30 years ago. But, there's one rule in calculus that called, product rule. It's a product rule. When you are taking derivative of a product of two functions, right? You have to split them up, and you have the first term is, you take the derivative of the first function times the second function plus derivative first function times the derivative of the second function. Okay, it's called product rule. So if we follow the product rule, then this is, basically what, like this, derivative of, d and b, d times, this is not times, this is modified duration, right? D star times b. So first we'll have to take the derivative of the d star and multiply it just by b. So that's it. And second, we have to multiply just the first function, which is d star derivative, right, times the derivative of the second function. And the derivative of the second function is, dB over dy, right? dB over dy. And what is dB over dy? That's exactly the definition of duration, right? So we end up with duration, which is, duration squared, right? And then, and this is, what is left is like, d star b, the modified duration, d star b, right? So I think there should be a I will still need b here. That was, yeah, that was what the original, yeah, that should be there. Now, the next, how do we, okay, if we found, if we found the formula for convexity, but how do we use that? Well, duration or convexity, whichever it is, what is the purpose? What's the purpose of using them? The purpose is to predict the change in bond price when there is a change in interest rate, isn't it right? The when there is 1% change or whatever percent, incremental change in interest rate, how much will the bond price change? Okay, so actually, the operational form of convexity is, like this. Change in bond price is B, the bond price, times C over 2 times, change in interest rate squared minus, duration times change in interest rate. And then at this point, you get to scratch your head. Well, I can understand that there is a quadratic component in convexity, because I can see at least there is that's quadratic. Duration is in second order. But how does it come to this is convexity, right? C is convexity. Why do we divide it by 2? And also, if we can write it this way, we can also write it this way, right? Because we divide both sides by, and then this becomes, percentage change, right, in bond price. Percentage change in bond price, right? I mean, that's percentage change in bond price, but this is, yeah, in dollars, right? This is in dollars. Okay, this is a dollar change in bond price, right? And then this is percentage change in bond price. Now, so the question is, why quadratic? Where did that quadratic equation come from? But first of all, remember the curvature, the convexity, or the curvature is not second order originally, right? Curvature is not second order. It's actually exponential function, right? Continuous compounding, right? So that's why we used, Euler's number, right? Okay, remember that? So it's not second order. You might wonder, oh, that's second order, that's quadratic. No, that's time. That's only time, not the time is not the curvature, right? That's not even, time in like, chronological time. It's just uh, time period, right? Coupon payment period, right? Time here means, coupon payment period. First coupon payment, second, third, fourth, that kind of, ordinal number, not cardinal number, ordinal number, right? Uh, the ordinal number of uh, coupon payment, right? So actually, it is, it goes through a process called Taylor series expansion, Taylor series expansion, or Taylor series approximation. What is that? Oh, it's if I went through all that, this is basically um, finance people don't care about this. I mean, it's only economists and mathematicians care about this. Uh, you know, they just in CFA exams, this is all you need to know. They don't need to uh, worry about how using the product rule or anything like this. They don't need to worry about that because they only use the application. They only use it. They don't make it. But who made it? Economists, right? And that's why there's math, so much math, economics. It's basically math, applied math, right? Math applied to uh, the economy, right, and society. Um, so a Taylor series expansion is a technique to approximate any nth order function, any nth order equation. If it is like I mean what I'm saying is any x the Taylor series expansion is basically the technique to approximate an exponential function approximated as um, nth order, any desired nth order equation, any desired nth order equation. So I'm not going to go through specifics of that step by step, but so if you want to approximate into third order, exponential function into a third order function, third order equation, you can do that. Fourth order, you can do that. Second order. I mean, we don't need third order, third order. Why? Because third order is not. I mean, we need second order is enough. Why? Because third order is like this, and we don't have this type of right. Third order is basically right. We only need. So this thing was a little too big, I guess. We only need to approximate it as second order because that's okay. Third order is like this. I forgot the name. I forgot the name. There's a name to call this third order. I'm sorry, this is sinusoidal. I'm sorry, that's sinusoidal function, sinusoidal, sine, cosine, right? Third order is not like that. Actually, third order is Third order is like this. But, we don't need that because we need only, curvatures like this. Second order, right, or quadratic is enough. Quadratic approximation is enough. So through Taylor series expansion, we come to this conclusion, right? Which is or this, okay? And then so we need to then do the how we apply this. Look, the application is obvious. If the equation came to this form, what does this do? What does this tell you? Oh, if we know the convexity, right, and we can predict how much the bond price will change, right? Because we have, a convexity, we have duration, and then we have interest rate, right? So interest rate change, so we plug in interest rate change, we plug in, convexity, plug in duration, plug in interest rate change. We can calculate the percentage change in the bond price. We can get, the change in bond price directly. Okay, so that example we're gonna do in the next video. Okay, together with Excel. That's it for this segment, and I will see you guys in the next video. Thank you. Stop recording.